Yo creo que voy a tener que... No hay streaming, no hay streaming.
Ya. Eso que la atracción de nadie, podría.
No sé qué le pasa. Ahí está transmitiendo.
Ah, pero está la presentación está pública. La compartimos.
Pues eso, mándame la presentación y me lo voy avanzando. Y que se vaya escuchando el micrófono y esta cámara.
¿Se escucha?
Sí, se escucha perfecto.
¿Escucha el micrófono?
Sí, porque tengo este.
Ya, pues está el link que está ahí. Está la presentación ahí.
No lo podéis copiar ya.
Bitly,
Ya, díctame. Bit.ly
ML,
Three ways.
ML.
Ah, mira tú. Perfecto.
ML3.
Waze. Mándale ese por favor.
Listo.
Ya.
Yo lo voy.
Cuando tengáis el link, tíralo al.
¿Alguien tiene un mouse inalámbrico que me preste? 400 informáticos en la sala.
un mouse?
Nacho, ya ahí hay un mouse inalámbrico. Excelente. Vale, comprar. Y el Bluetooth. Ya. ¿Alguien tiene un USB? ¿Más fácil? Sí, estamos cortos de tiempo. Listo, ahí está. Vale.
Va a terminar apenas listo.
Hola chicos, ¿cómo están? ¿Todo bien? Primero que todo, muchas gracias por venir. Me alegra ver la alta convocatoria acá y que hayan venido a esta mitad. Para los que no me conocen, yo soy Sebastián, uno de los iniciadores de la comunidad, que ya tiene más de 800 personas, así que estoy muy contento por eso y bueno, y todos los días todos ustedes están compartiendo y ayudando a los demás. Y por ese lado me pone muy contento ver cómo ha crecido esta comunidad y cómo ver que este es uno de los meetups más grandes que hemos realizado, junto con el otro que realizamos acá en la universidad, hace un par de meses atrás. Así que, bueno, más que nada acá lo importante obviamente acá son las presentaciones de los chicos y Mr. LAK, thank you very much for coming here to our country in this complicated moment. So I really appreciate that. Entonces voy a dejar a Manuel para que pueda explicar un poco cómo van a ser estas presentaciones y eso más que nada. Muchas gracias por venir. No le quito más tiempo.
Bueno, buenas tardes, gracias a todos por venir. Les cuento cómo va a ser la dinámica. La cosa de la presentación ahora toma alrededor de entre 45 y 50 minutos. La idea es que después tengamos una sesión de Q&A, de preguntas y respuestas. Va a estar Leo por allá, va a estar Stefan por acá, en ayudarnos en que las preguntas las hagan en español si no saben hablar inglés, y nosotros los ayudamos con el tema de la traducción. Por favor, no sean tímidos a la hora de hacer las preguntas. Yo creo que muy pocas veces tenemos la oportunidad de tener personas como LAK acá en Chile. Él es el líder de AI y ML en Google Cloud. Entonces, preguntemos lo que encontremos pertinente preguntar, obviamente, y nosotros los ayudamos en caso de que tengan alguna duda o tengan algún problema con el idioma. ¿Vale? LAK, feel free.
I didn't understand anything he said, but I heard so I assumed he said that I knew something about AI. Cool. Those are my slide link. So if you want to have access to the slides, you can get them there. So today I'm going to basically talk about 3 easy ways to do machine learning. So one of the common questions that we often get when we say about machine learning is that the frameworks are changing a lot. Like, where do we start? What is the right thing to do for a particular problem? So rather than tell you the answer, I'll basically walk you through a story, right? So I'll basically say, I'm going to solve a problem. I'm going to do it 3 different ways. And I'll kind of demonstrate to you why the advice that I'm going to give at the very end. So 3 ways to do machine learning. But of course, let's just start very quickly by saying, what is machine learning? Now, I'm not going to do too much math. Instead, I'll explain machine learning using this idea here, right? Suppose we did not have machine learning, and I gave you 2 arrays of numbers. The first array of numbers corresponds to the image on the left. The second array of numbers corresponds to the image on the right, right? And the numbers could be colors, for example, right? So, and I said, given this array, is this an apple or is it an orange? How would you do it? Texture, right? Or maybe much simpler, because it's a color, right? You could basically look at the most common color, right? And you might say, if it's the most common color is red, it's an apple. If the most common color is an orange, it's an orange, right? So you basically write a rule. And this is basically the way that we have been writing programs for the last 40 years, right? Whenever we had to solve a problem, we wrote a program. We wrote a set of rules, and we said, if this, if that, something else. Maybe we wrote a for loop to be more complex, but ultimately it boiled down to a human said, what is the logic that I will use to solve the problem? And let me teach the computer the same logic. Right? It was all about teaching the computer the logic that we use to solve the problem. Now, that's basically what we do, but of course, in reality, this is basically what we would get. Right? You would get an image that looks like this, and then our program would stop working, and we'd call it a bug, and then we say, how do you fix it? And then she was ahead of me there. She would say, well, let's go ahead and use texture. So instead of picking the most common color, let's find the variance of this. If the variance is high, it's an orange, and if the variance is low, it's smooth, it's an apple. So in other words, we write one more rule. Right? And that's the way we've always solved computer problems. We write rules, we write some logic, we go put it out into production, something happens, it doesn't work, we add one more rule. Right? And we basically build up these programs that consist of all of these rules. Okay, so that's the way we've always done it. What does machine learning do instead? Machine learning says, instead of you teaching the computer your logic, show the computer a whole bunch of correct answers. Right? Show the computer a whole bunch of images, some of which are cats and some of which are dogs, or some of which are apples and some of which are oranges, and say, hey computer, go figure it out. Right? And the computer basically learns based on those examples which one is correct. Right? It learns some idea of the logic. But the whole point here is, with machine learning, you are not trying to basically teach the computer your logic. You're trying to basically show the computer large examples of data that correspond to one or the other. And so we call that training, right? So where you have a bunch of examples with the correct answers for each, and then you tell the model to go learn it. And then once you have your model, the idea is that you can give it an image for which the label doesn't exist, and you apply that model to that image and you get the right answer. So that's prediction. Right? So that's the basic idea of how we set up machine learning problems. So why is this great? It's great because in traditional programming, every problem that you need to solve, you need to write a new program. Right? Suppose I said, I need to basically compute the tax rates right? Given all of the income and expenditures and everything for a business, you will write a program to do that. If I need to compute how long it's going to take to go from this city corner to that city corner, I would write another different program to do that route navigation. In machine learning, these two are the same problem. They're both regression problems. If I have enough examples of tax records, or if I have enough examples of routes that people have driven, it's the exact same model. I mean, that's what makes machine learning very exciting. The code is the same, you're just training it on different data, right? Which is fundamentally very different from the way we've always solved problems. Okay? So let's take an example of something that's not images. Let's say that you're this company that needs to figure out how much it's going to cost. It's like you have to go to a car auction and you need to figure out, should I buy that car or should I not buy the car? And it depends on how much the car is going to cost to repair. Okay? So what could you do? The old way to do this would be you will write a bunch of rules. So go look at the car, look at the tire, look at the windshield, look at the engine, see if it's leaking, write a whole bunch of rules to figure out how much it's going to cost to repair the car. The machine learning way of doing it, how would we do that? You have examples. So assuming you have been in this business for 20 plus years, you've bought a bunch of cars before and you've repaired them. So you have in your data warehouse information like, I bought the car for $43,000. I spent $1,000 on it for repairs. It was a truck. It has not been in an accident. It was made in 2012, and this is what the mileage was. Right? You have that data. So now you basically say, let me take all of this data and use it to train the model to predict the repairs. Now, the idea then is, we've trained the machine learning model. The next time we go to a car auction, we know all the other information, and we input that, and we get an estimate of how much it will cost to repair the car. There is no logic here anymore. It's all about knowing the prior data. It makes the way you approach a lot of problems very different, right? You approach them from the perspective of data rather than from the perspective of logic. So having said that, once you have that, then the idea is that somebody can go in and say, okay, if I buy a car for $43,000 and there's no accident, it was made in 2015, and the odometer reading is this much, what's the cost of repairs going to be? And we will get a cost of repairs. Right? That's the basic fundamental idea behind the whole ML setup. Okay. So having said that, let's now get into the meat of the talk, which is to solve a machine learning problem 3 different ways. Okay, I'm going to solve the ML problem 3 different ways. And the problem I'm going to pick is going to be a pretty complicated problem. Okay, a text classification problem, which is today one of the hardest ML problems. And we look at how to solve it with 3 different ways. So what's the problem? The problem is this. I'm going to basically, I have this thing where if I get the title of an article, okay, I just get the title of an article, fit with US fitness tracker, etc. I need to figure out, was it published in TechCrunch? Was it published in GitHub? Or was it published in the New York Times? Okay. So given just the title of the article, I want a machine learning model to tell me where this article was published. Okay. So let's take a guess. Unlikely partnership in house gives lawmakers hope. Where do you think it was published? New York Times. How about the second one? TechCrunch. How about the third one? GitHub. Everybody okay with that, right? Yeah, that's where it was published. Now, write a program to do that. It's hard, right? It is super hard in the old way of doing things. If I told you how to go write a logic program, explain your logic to the computer so you can do what you just did intuitively. It is, I'm sorry?
Naive bias?
I'm sorry? Naive. Yeah, you can do naive bias, but whatever it is, you have to kind of, the logic becomes really hard. If you have to write if-then rules to basically, this is the logic that I want you to follow, to say this is New York Times or not New York Times, it becomes really hard, right? Whereas with machine learning, what do you have to do? What do I need?
Data.
Data. What data do I need? Titles. I need to have enough examples of titles from New York Times. Is that easy to get?
Yeah.
Oh yeah, right? They publish thousands of articles a week. I can obviously go get enough examples of New York Times titles, enough examples of TechCrunch titles, enough examples of GitHub titles. And that's all I need, right? Imagine the amount of time it takes from a data perspective versus from a logic perspective. So that's basically the issue. So that's what we're going to do. We're going to train 3 machine learning models, right, to do this. And we're going to train first a BigQuery ML model in SQL. BigQuery is the data warehouse on Google Cloud. So our data will be in BigQuery. We'll just train it using SQL. The second thing that we'll do is we'll use AutoML, which is just completely throw the data at it, let it go, let it spin, replace all of our work with compute and see how it does. And the third thing, I'm going to use Keras and TensorFlow. Okay, I'm going to use 3 different ways, and then I'll end up with how do I choose between these 3 different approaches. So, but before I get going with all that, well, as with any software, I've got to make one decision. Should I even build this thing? Why? Because if I can buy it, I should go buy it. Right? Inevitably, buying software is often a better idea than going building your own. So there, in terms of ML, the way you buy software is to use a pre-trained machine learning model. And the pre-trained machine learning model in this case is that it's a text classifier. So I need to be looking at the natural language API. So that's cloud.google.com, natural language. And fortunately enough, this thing does already exist. And it provides a way for me to go ahead and try the API. So let me go ahead and try the API. So unlikely partnership in house gives lawmakers. Will this pre-trained model tell me that this was from the New York Times? So I hit analyze, I confirm that I'm not a robot, and boom. What does this tell me? It tells me that partnership is a noun and house is a noun and border deed and lawmakers, etc. It also tells me the sentiment of it, which is pretty neutral. It tells me the syntax, where is the adjective, where is the noun, etc. And it tells me categories, but it doesn't know that this is from the New York Times. Right? So yeah, pre-trained model is not going to work. It's cool. I can use it as an input to other models if I want, but this by itself is not going to solve it. So I'm back to square one. I have to go solve the problem myself. Right? I have to train a pre-trained model. So in this case, we need to build a custom model. So let's go ahead and build it. The first model that we're going to build is with BigQuery. So with BigQuery, the idea is first, we get our training data using SQL, and then we create a model specifying what the type of the model is. Then we evaluate the model, and then we predict using the model. Okay, so this is like a standard ML workflow. So how do I get the data? Well, I could have gone ahead and scraped New York Times and TechCrunch and GitHub, but I'm kind of lazy. And I realized that there's a data set called Hacker News, where people post articles. They post the URL of the article, and they post the title of the article. So what I did was that I can go in and I can say select URL and title from that data set with where the length of the title is greater than 10 and the length of the URL is greater than 10, just to be making sure that they are reasonable enough. So let's go ahead and try that. So go down here and go into BigQuery, and we can say try that, run it, and it will go ahead and pull out a data set, okay, that looks like this. YouTube.com, Whitney Houston gone wrong, metropoly.co.uk, mobile first is dead, dasboom.com, whatever, covertimes.com, New York scripted from around the world, etc. So now I can go to this URL and I can pull out cover times. Okay, how do I do that? I can basically use some regular expression magic. So that's the next thing that I'm doing. So I'm basically going ahead, let me do that, go down here. Okay. So instead of just selecting the URL and the title, I'm going to basically now do a regular expression replace from the title, removing all the special characters, taking the URL, removing all the dots and slashes and all that. Regular expressions I call them, you write it once, you don't read it again. You can understand it. Okay. But essentially what I'm doing is I'm taking that URL, I'm pulling out just the middle part of it. So I'm doing all of that, and then I'm basically splitting the title by word. And I'm basically saying word 1, word 2, word 3, word 4, word 5. So I have the first 5 words of the title and the source of the article. So let's go ahead and run that. Okay. And this will probably take a few seconds. Let's see. Okay. So it took about 8 seconds. Process the entire data set. And it turns out that there's an article called Expose SPS as Web Services. And that's from GitHub. Okay, so that's my data set. I have my target label and I have my 5 inputs. Each input is a word. Fair enough? So I have my training data set. I'm now ready to go. I take that training data set and I add 2 lines of SQL to it. As I create or replace a model, the model is called text class. The model type is the logistic regression. That's my classifier. I have other model types that I can use. And then I say that my label column is source, everything else is an input. I take that, I run it. This will probably take about 3 or 4 minutes, so I'm not going to do it on stage. But once that's done, what I'll get will be in advanced data. I'll get my text class model, and this model, right? It will basically say this thing got trained, that is a loss curve, that's an evaluation curve, this is how long it took to train each iteration. So each of these is about 30 seconds, so 1, 2, 3, 4, 5, about 2.5 minutes. Right? It trained the model, and basically I can go ahead and look at the evaluation, and it tells me the precision, it tells me the recall. It also gives me the contingency matrix, which is kind of useful. And this one says that it got GitHub as GitHub correct 89% of the time, New York Times is New York Times correct 71% of the time, and as TechCrunch 23% of the time. So the confusion is between New York Times and TechCrunch. Okay? So about 23% of the time it gets New York Times articles wrong, it gets them as TechCrunch. But point being, you write SQL, you basically add a couple of lines of code to train the model, 2 to 3 minutes later you have your trained model. So super easy to create a machine learning model using BigQuery ML. So you do that. So we've created the model. What I just showed you, I can also do select star from ML and evaluate, get all of those things. But the key number I want you to remember is this, 0.79. Right? I got 79% accuracy on this data set, primarily because it got confused between New York Times and TechCrunch. Once I do that, I can also now go ahead and do a prediction. So I do select star from ML.predict where Fitbit's fitness tracker is. Fitbit's fitness tracker is, because it's from TechCrunch. That's a predicted source. Pretty cool, right? Government shutdown leaves workers reeling from the New York Times. The unlikely partnership in House gives from the New York Times. Downloading an Android Studio project, it gets it wrong. It's actually from GitHub, it says it's TechCrunch. But then we'd expect that, right? It's 80% accurate, we tried it 4 times, it got 3 correct and 1 wrong. Makes sense. Fair enough? Easy? Cool. Okay. So that's one way to solve it. You do it all in SQL, right? And it's a text classification problem I just did. It's a hugely hard problem, and I did it in SQL, and I got pretty decent accuracy out of it. So the next step is, okay, why do I have to even write all this? Can I do AutoML? Okay, what is AutoML? AutoML is essentially GUI driven, right? As long as you have your training data set. I had to do all the hard work to create the training data set. Okay, there is no shortcut to that. I had to write those regular expressions. I had to do the matching, munging, data cleaning, everything that I had to do for BigQuery ML, I still have to do. I have to have a clean data set. But once I have the clean data set, rather than limit myself to logistic regression or simple DNNs, I can go give it to AutoML and say, do neural architecture search, try really complex models out there. And rather than limit myself to treating each word as being independent, I can say, hey, AutoML, this is text. And it will do BERT, and it will do word embeddings, and it will do all of the nice fancy NLP techniques on the data. It will try out different hyperparameters and do all of these things. What is the drawback? With BigQuery ML, it took me 2.5 minutes to train a model. With AutoML, it's going to take me 24 hours. Okay. So instead of me doing the work, a computer is going to do the work for me. Right? It's going to throw everything at it, try every possibility, and come back and say, I've tried everything, here's the best for you. Okay. That's basically what AutoML does. So basically, it gives you best of class accuracy. In every problem that we've tried, it tends to be in the top 10% of categories. Okay, so not the best, right? Not the very best, but in the top 10%. And these days now, what we're discovering is that pretty much every Kaggle competition, people do AutoML and use it as the input into their model, right? They build on top of AutoML. That's the only way to survive in Kaggle now, right? You build on top of AutoML, which is normal, right? That human plus computer is always better than just computer or just human. Okay? And what this is that it's an extremely accurate method, but the reason it takes 24 hours is that it's computationally hugely expensive. How expensive? Okay, this is basically talking about computational requirements, and this is a logarithmic scale. So between something like AlexNet and Dropout and the simple model that we might build and neural architecture search, it's about 300,000 times. It's tremendous amount of compute. But what do you get for that? What we get is a very easy way to do it. So once I have my BigQuery data set, I can just point AutoML at that data set and say, hey, here's my data set, I've loaded it all up. Okay, let's see if I can find it. I can go into my data set. So it should be somewhere here. I can go into AutoML, natural language. Yes. There we go. AutoML class text classification. And I've already trained the model, so it should find it hopefully. And there we go. There's the article source model that I trained. And essentially all that I had to do was to point this GUI tool at my BigQuery dataset, and this is the text item in the dataset, the URL, and here's the source. I mean the source and the title, source and title. So all of these things, there are 35,000 GitHub, 26,000 New York Times, etc. And then I move into this tab and I hit the blue button. Okay. And 24 hours later, basically I get a precision of 94.7%. And when I go and look at the evaluation, I should basically have pretty much the same kind of UI that you saw in BigQuery with the contingency table. Okay, so go down there and there it is. But notice now that these numbers are 95% and 82% and 83%. Right? So the overall, what this ends up doing is that I get an accuracy of about let's see if I have it here. I get an accuracy of 86%. So remember what I got in BigQuery ML? 79%, right? The AutoML I get about 10% better. Okay, so I get 86%. So what did AutoML do? It basically did feature engineering. It did architecture search. It did hyperparameter tuning. It chose a model. It ensembled a few of the best models and then it basically distilled it, combined them, and exported them for serving. Did all of that. I have an API at the end of it. So that's the second way to do it. And then once you get the evaluation model, you can look at it and say, okay, we got 86%. And to predict with a model, it's already a online thing. So I can basically go in and type in, government workers, read leaves work or whatever, and say predict, and it comes back and tells me it's 99% pretty straightforward. But again, don't lose track of the fact that I still have to do the work that I did for BigQuery ML, which is to create the training data set. Once you create the training data set, BigQuery ML 2.5 minutes, we get a reasonable model. 24 hours later, AutoML, you get a great model. So second easy way to do it. But third, say, okay, no, this AutoML business is all too automated for us. Let's build it ourselves in Keras. Right, the deal with me, you have to remember that AutoML, the basic, at the end of the day, it is basically saying, forget about thinking and throw a bunch of compute at it. Okay? That's basically what AutoML is doing. Okay? It's replacing compute. And if you don't feel bad about losing to your computer at chess, you should not feel bad about losing to AutoML on machine learning. It's the same kind of thing. Right? It's basically an exhaustive search, something that you probably don't want to be sitting there and doing, and it's doing. So let's not do an exhaustive search. We're smart. Let's build a good model, right? Based on what we understand about the data. So that's what I'm going to do in Keras. So my basic idea is, first of all, these are sentences, and when someone talks about border deal, the word border and deal together is something important. So this combination of words is important. How do you do combinations of things? Spatial correlation in machine learning is a convolutional filter. So let me go ahead in Keras, let me add a convolutional filter. Okay. Now, if I have border deal in part of a sentence and something else like leaves workers, leaves is not such a great word. What I want to do is to take the maximum of the trigger from each of the filters. So once I do the convolutional to get groups of words together, I take the maximum triggering, and then I take those maximum triggers, and this one is just 2 words at a time. All right. So what I now do is that I do another convolution to get 2 + 2, 4 words at a time. But this time, now the sentences are getting long, and I don't want to just choose the highest ranking. I want to start doing averages among them, so I get the beginning part of the sentence, ending part of the sentence, etc. So I do a global average, and at the end of it, what I need is a single classifier, so I end up with a dense. So that's basically the reason why I did a convolutional, max filter, another convolution, global average, and a dense. Great, but there's so many filters here, it's going to overfit like crazy, so I basically add in a few dropouts to reduce the overfit. That's cool. But the problem is that convolutional filters require numbers, and what I have are words. So how do I turn a word into a number? I need an embedding. So I add an embedding filter. So this is how I would do it if I were thinking. So I basically put these layers together, and in Keras, it's as simple as create a sequential model and take that diagram, create an embedding, dropout, convolutional, max pooling, convolutional, global average. Right? Add each layer, that's my model, compile it, model.fit. Right? And 20 minutes later, it's all trained, and I have my model. Okay. So great. So how do I train it? Well, I can just take my model, put it in a Python package, and say, hey, G-Cloud, just train this model for me. And it goes ahead and trains, and somewhere in my log, at the final end, I get my accuracy of 81.6%. It's nice. I got better than BQML, but not still 86%. So, okay. Once I have that, I can just predict the model using a REST API. I deploy the model, I basically send a particular string to it, and it's going to tell me where it was from. I can also load that model that I just trained into BigQuery, right? Model type is TensorFlow. And then I can basically do my ML.predict. So notice what I've done. I've trained my model with TensorFlow. I can load it into BigQuery, and I can then just predict with it as if it were a BigQuery model. So I can mix and match BigQuery and TensorFlow. But let's get back to the question that everybody's asking. I seem to do something reasonably sophisticated. Why did it not get good performance? Why did AutoML give me 86% and my fancy Keras model only gave me 81.6%? It all comes down to this. This is probably my one graph that if you want to take away, like you walk home today and say, what did LAK talk about? I want you to think of this graph. Okay, this is what I talked about. So let's walk through this graph. So this is the error rate. Okay, in this case, it's a translation model, but pretty much all machine models behave very much the same way. Okay, so that's the error rate, and this is the data size. Okay, so the error rate goes down. Notice it's going down linearly, about 0.04 for each trigger. But what's about the data size? Error rate goes down as data size increases, but what's going from here to here?
Exponential.
Exponential. It's doubling. So you want to go from here to here, you need more data. But how much more data? Twice as much data. 4 times as much data. 8 times as much more data. 16 times, 32 times, 64 times. That's machine learning. 10% more data is not going to get you anything. Okay. So if you want better models, you need more data. Okay. And when you've always heard people say, I need more data, right? But this is the actual more data. What do you mean by more data? We need 64 times more data, 32 times more data, right? Not 10% more data. Okay. So now you're a business person, you have $1 to spend, okay? And the difference between these two curves is that this is one model, this is the more fancy, right? Better model, more sophisticated model, has more parameters, okay? So you have $1 to spend, and that dollar you can spend to basically build a better model, or you can spend a dollar to collect twice as much more data. Where should you spend the money? Suppose you're here, should you spend the money collecting twice as much more data or building a better model? More data. More data. Suppose you're here, should you build a better model or collect twice as much more data? Twice as much more data. Suppose you're here, better model or twice as much more data? Still twice as much more data, right? Here, better model, twice as much data is getting to be close. Once you're here, better model, twice as much more data, it's even. A lot of people think they're here, spending a lot of time on building better models, when you're actually here, when you should be collecting more data. Okay, so the biggest mistake that people make in ML is forgetting where they are on the curve. Okay, so why did AutoML do better then why am I showing this graph to say this is why AutoML did better than my sophisticated model? It's because in my model, all I had were my 100,000 examples that I trained it on. Whereas AutoML is basically doing a transfer learning on things that it has trained on a much larger data set. And it's pulling all of that knowledge of English into my training data set. Like I said, it's taking advantage of things beyond my particular data set. So it's not just about the hyperparameter tuning and not just about the computation. Those help, but not to this extent. The transfer learning and the larger data set also helps. So, what's the point of my talk now, right? So having walked through this, let me kind of grossly simplify that this is what the point of this is. So when you're starting ML project, what should you do? quickly experiment using BigQuery ML. Use it to formulate your machine learning problems. 2.5 minutes a model is exactly what you need when you want to try a bunch of stuff out. Right? You try things out very quickly, get things going, figure out what features you need, figure out if you need to get more data. And by more data, I don't just mean more rows. I also mean more columns. See if you can join in another data set, build more data, right? Do all that. So that's what you should do first. Once you finally formulated the ML problem, created a data set that works well with BigQuery, point AutoML at it and say, hey AutoML, here's my data set, go, right? So one time deal, 24 hours, you get a great model and you're good. Then you continue collecting more data. And every time you have twice as much more data, try your custom model. Okay? At some point, and it will happen, at some point, your custom model will start to beat it. Right? Will start to beat AutoML. But that's going to be a while away. Right? And while you're still in the space of collecting data, don't waste time. Don't waste time building sophisticated models and playing around. That's just a waste of time. It's not going to actually help until you have enough data. Right? But each time you have twice as much more data, try building your own model. See if you can beat AutoML. So, start with some resources, couple of books, shameless plug. Okay, I have a book on data science and Google Cloud, and a very new book, just about a month old, on BigQuery. So both from O'Reilly. And thanks. Are we doing Q&A?
Where's mine?
Questions?
Yes.
Yes.
Well, the main idea at this point of our meeting is to understand whether you're doing in some of your industry, which challenges are you facing with this kind of initiatives. So we want to hear from you. Y de todas maneras, si es que hay un problema con el idioma, haré mi mejor esfuerzo en poder transmitir sus dudas hacia LAK. ¿Alguien? ¿Le paso un poco?
Hi, LAK.
Yes.
I have a question.
Yes.
You said that you need to feed some model.
Mm-hmm.
What is the model? How do you define the model?
How do you do the final model? Okay, so in this case, which is the final model that I would pick? Based on these accuracy numbers, I would pick the AutoML model, and that would be the model that I'll actually go ahead and deploy, so that every time somebody has a new title and I need to figure out where it was published, that would actually come from AutoML. So is that what your question was?
No, I was thinking in when you want to find some answer.
Yes.
Regarding the information that you have collected,
Mm-hmm.
You need to define the way on how you will get that model.
Right. So the model is essentially figuring out what your inputs are and what the output that you want is. So in this case, the output I wanted was where the article was published, and the input was the title of the article. Okay? So that is my model formulation. So you have to put your problem statement in terms of inputs and outputs. For machine learning, that's essentially the deal. You have to figure out what the inputs are that you will know at prediction time. So in the car repair case, the input would be the price I paid for the car and whether the car was in an accident and so on. And the output would be, after I bought the car, how much did I spend to repair it before I could actually use it. So input and output.
Okay. If you think in the fruit, what is the difference analyzing the information that you get regarding the color, the position of the pixels? I don't know.
Oh, I see. In the case of the fruit thing, The input would be the image itself, which would be the pixels, and the output would be what is in that image. Is it an orange or is it an apple?
Hi, LAK.
Yes.
How do you manage to like not stain the like how can I say the intelligence? Because for example, for me, my parameters could be like this is a cat, but for other person, no, this is another thing. How can you manage that?
I see. Yeah. That is a really hard problem, right? The problem is of labeling, and this often happens in things like medicine, right? Is this cancer or is it not? And it often happens that doctors will not agree. And so what you do in those cases is that you develop a protocol. So normally in radiology, for example, the protocol is that at least 2 people look at every image. And if the 2 of them agree, then that's acceptable. If the 2 of them don't agree, then it goes to another 3 people, right? And the 5 of them look at it, and then you pick the majority vote, right? So it becomes, you develop that protocol, and typically you do that at the time that you develop the experiment, and usually the protocol is defined based on cost. Because ideally you would have everybody look at 5 people look at every image, but it's too expensive. So you have everybody look at it, at least 2 people look at an image, and say if the 2 of them agree, then it's fine, it's done. If they don't agree, then you basically put it in a different bucket, and you have them, you have more people examine it. Sometimes if you want to save costs, you say if 2 people disagree, you don't use it for training. Okay? And
when you solve that protocol problem, you put it into the machine learning for future cases?
Not necessarily. You don't tell the machine learning model which were hard images and which were easy images. You just tell it the actual answer.
Okay. Thank you.
Sure.
LAK.
Yes.
Do you have any recommendations or best practice to keep the models working in the time? For example, to react or be sensible enough, for example, to reflect the social uprising in Chile or a no-show model?
Right. So that is a great question, and it's basically called continuous evaluation.
¿Se escucha bien? Sí, para que cuando repitan la pregunta o si hacen más preguntas que lo hagan con micrófono.
Yeah. So that's called the continuous evaluation. The idea being that as the model is predicting things, you want to log every input every request that comes to the model and what the model predicted. And then usually what happens is 1 week later, you know if the person bought it or didn't buy it. You know if the coupon got used or didn't get used. You know if the person was sick or didn't get sick, right? You know the actual answer a few days later. But then because you've been logging all your requests, you can now go ahead and do the evaluation, and you can plot the evaluation over time, and then you can see if the evaluation starts to drop. And that is something that on Google Cloud, we do that by default, right? So you basically get your continuous evaluation. You can basically turn it on. By default, you turn it on, and then any model that you deploy will actually do continuous evaluation for. We'll publish we'll store all of the incoming requests and the predictions into BigQuery, and then you can join against the actual data from a few days later and create a dashboard and then view it.
But you have to retrain the model, or it's part of a continuous evaluation?
Okay. That's a different question, right? Should you train so continuous evaluation will tell you if the model is going bad, right? That's all it will tell you. At that point, you have a decision to make. You can decide that the model has gone bad, and so I'm going to retrain the model. The second decision that you can do is that you say, I'm not going to retrain the model, I'm going to fine-tune the model. And that's a separate thing. The third thing that you can do is that you can say, I'm going to ignore it. Okay? So let's not worry about the ignoring bit. Okay, so the difference between retraining and fine-tuning is that retraining, you basically say, now everything has fundamentally changed. I'm going to throw away the old data. I'm going to train only on the new data. That's what retraining is. You retrain on this new situation, or you retrain with an additional feature as an input. Okay, but you're training a model is a brand new model. But more commonly, what people do is called fine-tuning, because it's really expensive to keep retraining a model every time it starts to drift. So what fine-tuning does is that you have a deep learning model, it may have like 50 layers, right? What you do is that you keep the first 49 of them the same, okay? And then you train the last layer a little bit. More commonly, what you also do is that the model has been trained for, say, 50,000 steps. You now take the new data that you have and you train the model on this new data, but you only train it for like 500 steps or only for 1,000 steps. So the model, the learning rate is really small. So it's getting trained in the new data, but from the old stopping point for just a few steps. So it's starting to reflect the new data. And then like next week you get some more new data, you fine tune it again. And next week you get some more new data, you fine tune it again. And over time, the model starts to reflect the newer and newer and newer data, with the older data getting kind of forgotten over time. So that's typically the way it's done.
Thank you.
¿Seguimos? Salva.
Gracias. Yo quería saber, la tasa de precisión que mostraste corresponde en el caso de Natural Language al inglés, y si hay una ficha para los distintos idiomas considerando la semántica, el contexto temporal y el uso de las palabras de las distintas ubicaciones.
We would like to understand if that accuracy rate that you show is in the trained models, it is just trained by the now or English, or it depends also with other languages, because there are other challenges like semantics and other things in each idiom.
Yeah. So this was just an example, right? This was very much just an example because I trained on only 100,000 rows. It was very small. To give a normal language model would be trained on much bigger data, but we've done it for 80 plus languages. So Spanish is one of the easier ones. It's usually the second or the third language to get trained models on. So you should be fine in Spanish. It gets harder as you get into Swahili and Zulu and like much smaller corpus of training data. But you have enough books in Spanish that it's not a problem.
Okay. What about
Hey, LAK. I have two questions about the AutoML. The first one is, if I get a model, I train it for 24 hours, and suddenly I get more data. Should I have to retrain the model again the 24 hours?
At this point, we don't support fine-tuning AutoML, so you would have to retrain, but it's on the roadmap.
Okay. And the second one is this model from AutoML like black box? I can know more about it.
Yeah. So the AutoML model, when you train the model, you have two options. You can say that you want a download of the model, and then you get a model that you can download, or you can say you want a model that you're going to leave on the cloud, and those models are much bigger. Right, so the model that you can download will tend to be a gigabyte or less in size. The model that you leave on the cloud can be 10 plus gigabytes. Right, so you have to make the choice. But if you say that you want a downloadable model, you will get a downloadable model. Okay, and either way, the models can have explainability built in. So explainability is this idea that if you send a request, you don't just get the answer back. You also get information around what part of the input was most relevant to the thing that you got back. So if you send a title back, it will say the words that were most important for me to give you the answer back were these 3 words. It can, if you're doing something that is more structured data, AutoML can, like the explainability modules, can also give you things like if the person's income had been 8,000 pesos more, then they would have gotten approval of the loan, right? So it can give you that explainability on that one instance basis. But that is, no, that's separate, right? So any model that you deploy, you can get explainability of.
Hello. The mathematical models for weather prediction typically are not so good. How machine learning methods maybe behave to
so this is something, this is something I actually know a bit about, because before I joined Google, I did weather prediction for a long time.
That's an excellent question.
So in terms of weather prediction, there is like 2 types of ML, 2 types of weather prediction things. Things that are shorter than about 6 hours, which is where machine learning really shines, and things that are longer than 6 hours. That is typically where numerical methods like physics works. So on the shorter things, machine learning has been used for like a long time, right? So I've been doing ML all my career in weather. So 20 plus years we've been using machine learning for short term, like flood forecasts or lightning forecasts. So if like airports like getting closed for under weather conditions, those are all ML models. Okay, so those things, they work relatively well, okay, but on the very short term. The thing that you're probably thinking about is longer term, right? 6+ hours. Those are not machine learning at all. Those are numerical methods, and those are based on physics, and they're subject to what's called chaos. So that makes it very hard.
Yeah, I come from a congress about physics, and the typical modeling is using a system of differential equations. But I think maybe a hybrid model machine learning.
So there's a lot of research going on into hybrid models. There's a lot of research going on into what is called parameterization. So you run your numerical model and then you basically calibrate it using machine learning. So or you downscale it, you make it like shorter resolution. So it's machine learning getting applied in hybrid ways to solve the problem, but it's not, machine learning by itself is not going to do it.
Okay, thank you so much.
Hi, LAK. Thank you for being here. Don't answer me if there is a personal question. In your profile picture, I wanna question you. What is the picture of your profile?
The picture of my profile. Which one? Are you talking? Are you talking the tornado picture?
That one.
Which one? Oh, this one. Yeah. Yes. Okay. So that's actually a very interesting. Let me see if I can find the picture. It's a pretty cool story. I'm just loading up photos at google.com to get you the larger one.
Train them all.
So I'm searching for tornado, and there it is. Okay. All right. Download. All right. There. Okay. So this is a different photograph. Same day. But this was in Oklahoma, and that was a tornado. And that was the last tornado that I chased. Yeah. So the story is like this. I've been doing research on weather prediction for a very long time, and things keep getting better and better and better, right? So it used to be that you would say, there's where the tornado is going to be. It will take you about 3 hours, 4 hours before
You kind of think where it was, and you drive over, try to find it, and most of the time you were wrong, and nothing was there, and it'd be a very sad drive back because you had not seen anything. And this particular one, it was like 3:30 in the afternoon, and we looked at the radar and we said, hey, it looks like there's going to be a tornado there. Should we go look? So yeah, sure, let's go. So we drive out 30 minutes, we go sit in a parking lot and say, we don't see a tornado, where is it? And then it say, oh, there's a tornado, it's not moving. No, it is moving, it's coming straight at us. So we basically moved like 1 mile away, and we sat as the tornado passed through the parking lot that we were in. And that's when I realized that it was done, right? No more challenging you or anything. If you can predict it accurately enough, I should go do something else.
Thank you.
It's a fun fact.
It's a fun fact.
¿Quién más había
LAK.
Yes.
I have a question about data scientists. What do you think about data scientists for, 5 or more years in future? I mean, we have several tools in Google to making the job of the data scientist, you know? So what do you think about the future of the data scientist?
Okay. So
is it necessary in a company?
Okay. So first thing I want to say is, I don't want people to draw the wrong interpretation, right? AutoML did not just work. I had to create a training data set, right? I had to clean up the data. All of that I still had to do, right? I had to understand how to frame the problem. All that AutoML did for me was that it saved me a bunch of coding. Okay, I did not have to write the code. That was about it. Okay, the thinking I still had to do. The thinking it did not get rid of, right? So what you have to think of is like it simplifies the job of a data scientist. Maybe it makes it possible for more people to become data scientists, sure, right? And that's always a good thing, because the more people that can do the job, the more work there is. Right? If you're in a profession that only 5 people can do, by definition, people will not do that thing. Right? If you're in a profession where hundreds of thousands of people can do it, there will be a lot of jobs for that. Every company will be doing it. So you're better off in a profession where that is open for more people. Okay? We don't want to be in a profession where only 3 or 5 people in the world do it. Okay. So we still have to do all of the work of thinking, of framing the problem, of solving it. So what happens to data science to me in the future is that it becomes more and more about understanding the business and understanding the business problems and understanding how to talk to people and being more creative in what problems we are solving, and less about knowing how to code Python. I don't think that's a bad thing. ¿Pizza?
¿Más preguntas? Manuel y Sebastián fueron a buscar las pizzas. Así que están esperando.
Oh, it's weird.
More questions.
We would like to understand what is the future about the data in all companies, for example, Google, Microsoft, and other players important in the world. How are we going to drive the data? How we are going to...
What is happening? I think, probably the most exciting thing in terms of technology that's happening is the increasing amount of the way in which data is used. Where, imagine all the programs that we've been writing, and many of these programs are becoming data problems. And it's about collecting more data, it's about measuring things across the life cycle, of adding more things that you are collecting and saving and using, right? So the world is changing to be a data-driven world, with a lot of decisions being informed by data, right? Not made by data, not made automatically, but being informed by it. Which means that as technology companies, whether it's Google or Microsoft or Amazon or Oracle or anyone, we're all about how do we basically make it possible to get intelligence out of the data. Right? So this is something that everybody's working on, and again, that's a good thing. I don't think it's a good business if there's only one company working on it. It's a good business if everyone is actually actively working and competition is good.
Thanks.
I get this question. If you have an enormous data set, you can use data prep or in order to clean to prepare your model, or you have to jump into BigQuery, make some expression, regular expression thing, or you can clean it with data prep or use AutoML. Or...
Yeah, right. So as far as cleaning up your data goes, there are several choices in Google Cloud. The one that you pointed to, data prep, is a great one. It's basically UI driven. So it shows you distributions of every column. It allows you to correct things like telephone numbers and so on. It knows about common problems, about nulls and imputations. So you can specify rules and you can kind of fill them out. So that's one way. So that data prep tends to be really loved by business and intelligence people. Okay, so people who are very familiar with dashboards and UI tools, they like data prep. The second way to do it would be what's called data fusion. Data fusion is also UI driven, but the UI components here are now blocks of Spark code or Python code. And you're basically saying, I'm going to take this data, I'm going to apply this transform, this transform, this transform. I'm going to read from here. So it has a bunch of connectors built in. It knows how to read them, and then you supply a little bit of code here and there. You build that pipeline, and that pipeline runs on Spark or runs on Dataflow. Okay, so that's a UI-driven way of doing it. That tends to be loved by data engineers. Okay. The third way to do it is to basically write it all yourself in Dataflow or write it all yourself in BigQuery. That tends to be loved by programmers. Pick what you like. But you have to clean up your data.
Yeah.
However you do it, you have to clean up your data.
Hi. Can you talk to us more about TPUs and the benefits to use this kind of technology to train your models?
Oh, sure, absolutely. Let me see if I have a quick thing about what a TPU is. Quick deck on
No venía preparado.
Sorry?
You're very prepared to this question.
Let's see. I'm prepared for this because it's easier to show it with TPU. Okay. So a TPU, for those of you not familiar with TPU, a TPU is a Google-made chip. It's an application-specific chip for machine learning. And again, if you're not familiar with the way hardware has been going, for a very long time we had what was called Moore's law, right? That the power of the computer doubled once every 18 months. It stopped working about 6 years ago. Okay? We reached the limits of physics in terms of how much you could squeeze onto a single chip. And so computer chips stopped getting more powerful. So what did we have to do? Right? So now the only way to get more power from a chip is to start throwing away instruction sets. Right? Make the chip do less, but make the chip be more customized. And that's what ASICs are about. Application-specific chips are about basically saying, okay, don't think about it you being a CPU, you just have to do these 3 operations and do them very fast. Okay, and that's what an ASIC is. So a TPU is an ASIC. Okay, it's only for doing one operation very, very fast. And that operation is a 128 by 128 matrix multiplication. It doesn't do anything else. Okay, it does a 128 by 128 matrix multiplication, and it does it super fast. But it turns out that that one operation is at the heart of deep learning. Okay? And so by making that one thing really, really, really fast, we're able to basically get really good cost optimizations on machine learning. Not for anything else. So you can use TPUs for other stuff, but for this operation, it works very, very, very well, and you basically get power, right? So here's an example of what a TPU is. The first benefit of the TPU, right, is that you basically you can take multiple TPUs and put them into what is called a TPU pod, which is basically a group of TPUs. So the second benefit of the TPU is what that graph on the right shows, which is normally if you do distributed programming, if we have like one chip and you get some performance, say it takes 10 seconds to train something. If you had a second chip, will it now take only 5 seconds? No, it'll probably take like 7 seconds because there's some network overhead for communication. What a TPU does is that it basically puts all of the chips in a pod with extremely high networking between them so that it actually linearly scales up to the size of a pod. So it makes that pod very, very, very powerful. Why is this important? For Google, it's very important because a language model, a typical language model, German to English, for example, takes on a GPU, it would take about 48 days to train. Okay. 48 days. Right? On a TPU, it takes about 24 hours. Okay. So it's like that 48 times improvement is humongous, right? But it really, really benefits when you have these massive ML training jobs. Okay? So an example of customers who use this is a company called eBay. There we go. So this is a blog post from eBay. So on eBay, the idea is that when you take a photograph of the thing that you want to sell and you put it on eBay, they need to say, oh, this thing that you're posting, this must be a Pixel 2, and here's another posting for a Pixel 2. We'll copy all of the information for the Pixel 2 into this, make it easier to post. Right? That model is the image recognition model, and they need to keep retraining because the things that people sell keep changing over time, right? So they can't afford to wait 48 days to train that model. They have a humongous data set, so instead they use TPUs. Okay, so this is about training massive models where you need the power of that distributed training, and you need the power of like a single TPU chip being able to do that matrix multiply very, very, very fast. It's probably a longer answer, but we're waiting for the answer.
My last question. I want to know what should we do in order to be a machine learning professional?
What should you do to be a machine learning professional? Probably I'll talk about a few courses and so on that we can do, but don't lose track of the fact that the best way to learn is to do it, right? So you want to always do labs, right? And you want to always try things out. But good resources, a couple of them. There's a very cool site called Quick Labs. So Quick Labs has a whole bunch of these example labs and things that you can try out. So you can do Quick Labs machine learning, right? And basically, here's a whole bunch of things that you can do to try and learn from Quick Labs. And of course, I have to talk about Coursera machine learning. So on Coursera, there's a bunch of courses from Google Cloud on machine learning. Okay, so this guy. So that's another way to do it.
First of all, thank you for being here. I've gone through some of the courses on Coursera and Quick Labs and GitHub, and I've noticed that mainly they're using TensorFlow 1.x.
1.14, yes.
In your experience, now that we have TensorFlow version 2, are people slow to adapt to TensorFlow 2, or is there any reason why they're all...
We are actually updating the course. So if you go into courses, the one that you have been doing is under Machine Learning Deep Dive, right?
Yeah.
You'll notice there's a Deep Dive 2, and Deep Dive 2 is all of those labs converted to TensorFlow 2. We haven't recorded the videos yet, okay, but the labs are all updated to TensorFlow 2.
Okay, thank you.
You notice that is very, very, very recent, 23 hours ago.
Le quería recomendar a los chicos un video de LAK que se llama Cloud on Air, End-to-End Machine Learning. Está muy bueno, lo pueden buscar en YouTube después. Usa Code Labs, que es un similar a Quick Labs, para explicar todo el proceso de end-to-end de Machine Learning. I recommend to the people the Cloud on Air in end-to-end machine learning. This one. This is a very good video to understand every aspect, basically, of machine learning.
Right. And that's actually associated with the Code Lab as well.
Have a great actor, very famous.
So this one, okay, and so that's the one. I recognize this guy.
It's an exception.
And actually, there's a Code Lab associated with it as well. So it basically, this is TensorFlow 2.0.
Very good.
Perfecto. ¿Alguien más?
Ya venían con las primeras pizzas.
¿Ya llegaron?
Sí, ya llegan.
Aprovechado.
Could you use like a regression model, like natural language for neural network to learn something, or you could only do like conversion one, or you could like...
Yeah, you can make, there's multiple machine learning models, so you can do very traditional things like ARIMA, so on. You can also do regression, you can do classification, you can do XGBoost. So yeah, there's all of those are possible.
Yes. One month ago, we made a public announcement about quantum supremacy.
Okay.
Yeah, probably our audience would like to hear a little bit about that.
I'm not an expert in quantum supremacy, so I don't know. All I know is what I read in the newspaper. Sorry, I can't add too much more to it.
Déjenme ver, yo creo que estamos casi listos con las pizzas. So,
we're almost done with the pizzas.
Yeah, we're almost done with pizzas. We ordered some pizzas.
Oh, okay, very good.
Very good.
Thank you all.
Thank you.
Thank you, sir. Thank you, LAK.
Chicos, acaban de llegar las pizzas, están acomodando, así que si quieren pasan mientras. Hay regalitos de TensorFlow, si quieren aprovechar. La vegana. Después le vamos a sacar una foto.